Then we're going to start on talking about loading and the powertrain, and then in the following weeks we'll cover cornering and other instrument handling. So today we'll just look at the forces on a car. We'll talk about static loading and some of the equations you can use to come up with that. It's nothing too taxing. It's all basically level 1 dynamics, applying Newton's laws. Look at dynamic loading on the car, and then also talk about tractive force and the powertrain relationship between those things. Look at resistive forces and tractive forces and those sorts of things. If we take a car inside view, okay, clearly there are some forces that we can look at applying the car. And then obviously there are tractive forces, which is making the car go. Okay, you've got resistive forces, which is opposing the tractive force. And they're the things that resist the car from moving. Okay. And then in the vertical direction, you've got weight, which is pushing the car to the ground. And then you also have lift forces from the air flowing over the car, causing the car to rise up or down, depending on how you set up your car. So those are the sort of basic forces in the X and the Y directions. But we can examine some of them in a bit more detail. If we take the resistive forces, okay. There are some different components of those resistive forces. The one you're probably all familiar with is aerodynamics. Okay, there's resistance, and we call that FA for aerodynamics. Okay, and that's going to resist the motion of the car. Clearly, if we're moving through the air is providing a resistive force. The other one is rolling resistance. Okay, which comes from the tyres generally. Okay, that resist the rolling of the tyres. Okay, and then there's also due to going up or down the hill, that's going to be a resistive force as well. If you're going uphill, there's going to be a component of the weight that's pointing down the hill that the car has to overcome as well. So those are the resistive forces. The tractive force clearly must overcome those resistive forces for the vehicle to accelerate. Okay, and so you've got FR, which is all our resistive forces. There are these three things added up together. Okay. And Ft, which is what we call the tractive force, okay, minus the resistive forces, so this is our tractive force, minus the resistive forces, this nice acceleration is usually taken log. The sum of all the forces, okay, assuming x is in the positive direction, this direction, okay, tractive force minus resistive force is going to be minus the acceleration. That all makes sense, okay, is that clear? And so you can rearrange, you can put all these things in for FR, you end up with Ft, which is our tractive force provided by the engine, minus the area, the rolling resistance and the grade equals your mass on acceleration. Okay. So if you look at aerodynamics on its own, there's a picture. A couple of times I mentioned Myra being a services company. We'll look at the corner there, there's a Myra logo. This is the car being tested at Myra. In terms of aerodynamics, there's in a wind tunnel. Okay. Aerodynamic drag is made up of three different things predominantly. Okay. Clearly, as the air flows over the car, you're going to get turbulence. Okay, around the vehicle body, certainly at the back of the car, and depending on where there's sharp edges and things like that. Okay. Clearly, there's friction between the air moving and the car body. Okay. You get a boundary layer thing going on, so that also contributes, which is why if you think about air over a train, a long train has more drag than a small train, even though the frontal area is the same. And there's also, due to air going into the vehicle through the grille, and various other vents and things like that, obviously that also creates some resistance as well. Okay. And that's the sort of more or less how they fare up. The biggest, like I said, is this one here. Okay. Well, these are all encapsulated in this equation. Okay. We've got our aerodynamic force. Okay, it's 1/2 times by rho, which is the density of the air. Okay, that can be taken as a specific value. Okay, we've got this thing called the coefficient of drag, and that's where all these things are taken into account. The projected front area of the vehicle, so this is, if you imagine looking at the front of the vehicle, it's the area that's outlined by the shape of the vehicle, okay, and it's times by velocity squared. Okay, so you can see that velocity is quite a big impact, okay. If you go twice as fast, you've got 4 times as much drag, okay, which is why, you know, people say that you know, at 70 miles an hour you're going to get a certain amount of fuel consumption. If you go 80 miles an hour, it's not just a little bit more fuel consumption. You've got a lot more because you're going that much faster. Okay, so that's the equation that encapsulates aerodynamic drag, and that's the one we use. Okay. Projected frontal area, like I said, that's the view from the front of the car. And if you look up fuel consumption figures or whatever for different cars and stuff, often they'll state a certain number, okay, depending on the tyre width, because obviously that's the additional projected frontal area. Okay, if you've got wider tyres, you've got more frontal area, and those sorts of things. Obviously, tyres will have different roller resistances as well, so they will also impact on your fuel consumption. Roller resistance, okay, well that's, again, like I said, it's due to the deformation of the tyre, okay. As the tyre rolls, clearly it deforms slightly, okay, depending on the tyre pressures and the size of the tyre and all sorts of other aspects, tread design, that sort of stuff. Clearly, as the tyre interacts with the road, it penetrates, okay, and obviously if there's also, as the wheel is rolling, and so you've got some air circulation things going on around the wheel, and the slippage of the tyre between the tyre and the wheel. All these things sort of deforming slightly, okay, because the tyres are made of rubber. So rolling resistance is also sort of an equation with a bit of a fudge factor. So before we had the coefficient of drag, okay, the tyres do have this coefficient of rolling resistance, okay, and that's multiplied by the normal force on the tyre. Okay, so that's not the vertical force; it's the normal force. So it's the force that's perpendicular to the road. Okay, coefficient of rolling resistance and the normal level of the tyre. Okay. Now clearly, rolling resistance only impacts on the car when it's moving. Okay, you can't obviously have so if you're trying to sort of model a vehicle and you've got rolling resistance, you need to make sure that that's only applied to the car when the car's actually starting to move. Okay. Clearly, for aerodynamic drag, there's a V term in that equation, so obviously the V is 0, drag is 0, so that works. And some example CR values. For concrete or asphalt, so nice smooth road surface, you've got 0.01 as a typical CR value, okay, 0.015. If you're driving on gravel but it's rolled, so it's flat and even, then it's 0.02. Unpaved roads, 0.05 as a guess. And if you're driving on loose sand, you can see the numbers are going up quite a lot, 0.2 to 0.4. Okay, so they're quite significant. Driving on loose sand is clearly more resistive than driving on a concrete surface. And these are some examples of different roll resistances depending on tyre pressure. Okay, you've got different tyre pressures there. These are the coefficients of roll resistance, and then we've got the speed. And you can see the speed does have a sort of impact. Okay, the faster you go, the more resistive you've got. Okay, but generally, what you do is you take, you assume that it's pretty much flat. Okay, it's consistent. So, like I said, the faster you go, the more resistance you've got. But generally, we assume that it's not speed dependent. Grade resistance, well, this is clearly straightforward. If you've got an angle of the hill, we've decided that going uphill is a positive angle. Okay, clearly going downward is a negative angle. Okay, and you've got your mass of the vehicle. And as you did in level 1 dynamics, you can separate that mass into 2 components. One that's normal to the road, so mg cosine theta, and one that's parallel to the road, mg sine theta. And that mg sine theta typically is pointing down the hill, which is providing the right resistive force. Okay, going up the hill. So those are the 3 sort of equations we've got. We've got mg sine of theta being the grade. We've got white on the board. I can do the pen off. So FA equals 1/2 rho CVA V squared. Okay. We have F RL, which is our Warren resistance, which is C RR times by the normal load. And then we've got FG, which is the grade, which is simply mg sine theta. In the direction of travel. So those are the loads on the car when it's moving, but let's have a look at the loads when it's not moving, but it is on a grade, okay? So we've got this vehicle. I've drawn a line showing you what the height of the centre of gravity is. That will affect the loads on the wheel. Okay. You've got the normal load at the back wheels, okay, NR. Okay. You've also got a load at the front wheels, NF. Okay. And the distance between those points, NR and NF, is known as the wheelbase, that's L. Okay, so the distance between the front axle and the back axle. And then we've divided that wheelbase into C and D, which are the distances between the front axle and the centre of gravity point, and the rear axle and the centre of gravity point, and C and D. So C plus D equals L. Okay. And obviously, depending on the value of C and D, that's what your front to rear weight distribution. Okay. Cars with a front engine and front wheel drive and all that sort of stuff tend to have a more load on the front. C is shorter because the centre of gravity is towards the front. Okay. Cars with a rear engine, say, or mid engines and rear wheel drive, obviously the centre of gravity is going to be closer to the back, so your D is shorter. Obviously. Okay. So if we do some sums, taking moments about the rear tyre contact patch. Okay, so taking moments about here. Okay, clearly that we're saying positive is in the clockwise direction. We've got a load being transmitted by the centre of gravity. Okay, being resisted by a load at the front tyre. Okay. We've got this load, mg's cosine theta, which is this. This is also the positive direction, clockwise that direction. In fact, we've said the positive is actually anti-clockwise in this way. NF times by L, so those are in the anti-clockwise direction, minus mg cosine theta times by D, which is that distance there. Okay, and also minus mg h sine theta, which is
So is the engine in the middle on that?
Sorry?
For that example, is that in the middle? Yeah.
The engine? Oh, well, no, it doesn't matter.
Okay.
That will be given to you in terms of D's and C's, okay? That car in particular, that picture is an i8, it has got a bin engine car, but this is, like I said, that's immaterial. Okay, it's just a car. So you've got your equation here, you can rearrange that equation, solving for NF, which is the load on the car, okay, the load on the front tyres. And clearly you can do the moments about the front tyre contact patch to work out what NR is. Okay, and there's NR. And clearly if theta is 0, then obviously NF, this is the weight on the front axle, which is mg, which is the total weight of the car. And then you've got the proportion on the front axle is d upon L. Okay, because clearly if you've got a front weight bias, d is longer, c is shorter. So the weight on the front is actually d divided by L, which is that proportion as opposed to c divided by L. So bear that in mind. So let's have a go at the question. So here's the question. For a car with a mass of 1500 kilograms, travelling at an increase of 5 degrees at a constant speed, determine the normal loads on the front and the rear tyres, okay, if the centre of gravity is at a height of 0.6 metres above the road and a distance of 0.2 metres from the front axle. And it's given the wheelbase is 2.6 metres. So this is in-class question number 1. Okay. We've got a mass of 1500 kilograms. Okay, we've got a C of 1.5 metres. We've got a wheelbase of 2.6 metres. And so from those two values, we can work out what D is. It's 1.4 metres. Okay. A height is 0.6 metres. And we've got an angle, theta, of 5 degrees. Okay. And so we have our equation NF was mg d cosine of theta minus mgh sine of theta divided by the wheelbase L. Okay. And so we've got an mg in both of them, so I'm going to take them outside. 1500 9.81 divided by 2.6, and then inside the brackets here I'm going to put d 1.4 times by cosine of 5 degrees minus h, which is 0.6, times by sine of 5 degrees. Okay. And if you do that sum on your calculator, you should get 7,597 newtons. For the rear, there's a couple of methods. One is to simply employ this equation. So you can go through the process again. 1500 9.81 divided by 2.6. And you have C, which is 1.6 cosine of 5 degrees plus 0.6 sine of 5 degrees. $7,062 newtons being the value for the rear normal load. Okay. The other way to work out the rear normal load is to take the total load and subtract the front one. So NR mg cosine of theta, which is our total load, minus the front load. And so if you do that,